before we get started, do you guys have any questions? Oh, the light? Sure. Anything else? Just as a reminder, when you're getting to your homework problems in this class and in every other class, and when you get to work, it's always really important when you first get started to not immediately jump into the code, but to take a step back and think about what the heck do I want to be doing to solve this problem in the first place, right? My recommendation is to, one, say what it is that you want to do. Two, do some examples, practice by hand, right, and solve some problems. Make sure they're varied, make sure, they're somewhat interesting, make sure they test edge cases if you can think about them right now. Then once you do some examples, step back from the whiteboard or your piece of paper, whatever it is that you're doing, and ask yourself, what did I just do, right? What steps did I take to solve the problem? And if your answer is like, I just looked at it or I did it, you need to think a little bit more, because you can't tell the computer to just look at it or just do it, right? You have to give it a series of steps that it can follow to be able to complete the problem, right? When you're just looking at it, you're relying on your intuition of the problem to be able to get it done, right? And your amazing mental capacities of the human brain. Again, computer lacks that, so just think about what it is that you did and then go write those steps down, right? A list of coherent steps to follow as to what you did. Keep the steps broad, keep them general, and kind of forget that you know how to code, right? You shouldn't have any mention of types or lists or vectors or arrays or strings whatsoever at all, right? It should just be, this is what I would like to do, right? Keep your steps general, and if the step is a rather large step, perfectly okay. Just make that into another sub-problem that you have to repeat the process on all over again, right? And each of these major steps, when you solve it, will end up becoming a function when you write your code. Right? Once you have your list of steps down, go and reapply them to the problem. See if they work. And do what the steps say, not what you want to do. Right? Don't rely on your intuition at all. Do each step as you've written it down. After you've done that and everything seems to be working out great, then go implement it. But now you have some thing that you actually want to do, a series of steps. You can write intentful code, meaningful code, instead of just trying things to see if they work. Right? You have a plan, follow it, and write your code so that it reads like the plan. Use lots of functions to hide the complexity and make thinking about the problem easier. Rely on that abstraction. Once you finally got implemented, test it, see if it works. Is it doing what you expect it to do, right? And if it's not working, go run the debugger. See what's happening in your code. See what's differing from your expectations versus what's supposed to be happening, right? And you have your list of steps that you've written down, so you know what should be going on in each and every process, every part along the way. And then, fix the bug, repeat, rinse, recycle until you finally get the problem complete. Yeah, Mira?
I have a question for Alphabet, which is, when we're taking in the very long number, what type should it be? Because I was trying to make it into a bit set.
Stored as an unsigned integer. So since you're accepting arguments on the command line, they're going to be strings. Argv is an array of strings.
Right.
Convert each string to its numeric representation.
Okay, so make it into an unsigned integer?
Yeah.
Okay, and then the bitwise operations will work?
Yes, because you can't perform bitwise operations on a string because it's not the correct binary that you want to be working with. But once you have it in the numeric form as an unsigned integer, it will be the binary that you're expecting to work with.
I see, thank
you. Mm-hmm.
Also, after this, will we be able to do all the homework?
Probably after Thursday, you should be able to do all the homework.
Thank you.
Anything else before we continue on? Again, stop by office hours. Keep asking questions. They're good. They're great. They're going to help you learn. Last time we left off, we talked about how bit patterns could be used to represent different things, right? And a bit pattern by itself has no particular meaning, right? Context helps us figure out what we're supposed to be doing, right? This is kind of also showing up in that new alphabet problem, right? The representation for the number 8 is the same representation in our new alphabet for the letter D, right? They have the same bit string, right? But in different contexts, they mean different things. And you have to rely on that context to kind of figure out what's actually supposed to be going on. So let's talk about representing numbers, right? Integer numbers, to be precise, right now. So when we have the number 2,356, right? This is just shorthand notation for 2 times 1,000 plus 3 times 100 plus 5 times 10 plus 6 times 1, even if we've kind of forgotten that, way back when we learned it in elementary school. That's really what you're saying when you write a number like this, right? Or another way of writing it, it's 2 times 10 to the 3 plus 3 times 10 squared plus 5 times 10 to the 1 plus 6 times 10 to the 0, right? These bases are base 10 because we're the decimal number system, and we probably use the decimal number system because we have 10 digits on our fingers, right? So we take each digit that we have and we multiply it by 10 to the n, where n is its place in the number, right? Rightmost digit is the least significant digit, 0. Leftmost digit is the most significant digit on the far left. And as you move up, the numbers increase by 1. When you're in a number system, the largest digit that each digit you can have for each spot is that base minus 1. So since we're in base 10, we can have digits up to 9. If we were in base 20, we could have digits up to 19. If we're in base 3, digits up to 2. When we're in base 2, we have digits up to 1. There are definitely some other number systems, ones that we kind of use a bit frequently when we're working with the computer, which is hex, which is base 16, and there's binary, which is base 2. So base 2, again, digits can either have the value 0 or 1. Again, it's perfect for representing numbers in the computer system because bits can only have the value of 0 or 1. When we're figuring out what number that we have, it's just like the base 10 number, except we multiply by powers of 2 instead of by powers of 10. So if here's our 5, 4, 3, 2, 1, 0's place, so it's 1s, 2s, 4s, 8, 16s, 32s. So if we had 1, 0, 1, 1, right, that's 1 times 2 to the 0, plus 1 times 2 to the 1, plus 0 times 2 squared, plus 1 times 2 to the 3, right? Just multiply them powers. So that's 8 plus 0 plus 2 plus 1, which is equivalent to the value of 11 in base 10. Any questions so far? Should be fairly straightforward. So let's say we want to have the task of finding the binary representation of a number quickly. It's fairly easy to do with base 2. So you just write out the powers of 2 until you get to a value that's greater than or equal to the base 10 number that you want to represent. Working from left to right, check if the value at that spot is less than or equal to the base 10 number. If it is, you'll write 1 in that spot, and then you'll subtract out whatever the value of that number is from that position. If not, put a 0 there and continue on your merry way until you get all the way to the end. So let's say, for example, we wanted to convert 72, right, to binary. So we keep out writing powers of 2 until we get to a power of 2 that's greater than or equal to 72. So we have our 1s, 2s, 4s, 8, 16s, 32s, 64s, 128. So we stop at 128 because it's the first number that's greater than or equal to 2, or greater than or equal to 72. So are there any 128s in 72? No. So we put a 0 there. And again, with binary, since we only have a digit of 0, 1, it's either yes or no, right? And just checking if it's less than or equal to. So are there any 64s in 72? Yeah, 1, right? So you say, okay, I have 72. And let me open up idle here. So here was our number, right? It's 72. And now, since we decided to put a 1 in that spot, number minus equals 60. Oops, num equals 72. Num minus equals 64. So now our number ends up being 8, right? After the subtraction, after we put 164 there. So are there any 32s in 8? No. Any 16s in 8? No. Any 8s in 8? Yes. 1. So we subtract out our 8, and we end up with 0. So are there any 4s in 0? No. Any 2s in 0? No. Any 1s in 0? No. We've gone through all the bits, so we're done. And this is our binary representation for 72. Any questions here? Okay. Let's say you want to convert the value 59. into binary, right? Go ahead and try that out. I'll give you a minute, to work through it. Shouldn't take too long. Okay, so again, if we're following the process, the first thing that we would do is we'd write out powers of 2 until we get to a number that's greater than or equal to 59. So we go 1s, 2s, 4s, 8s, 16s, 32s, 64s, right? And at that point, we can stop. So are there any 64s in 59? No. Are there any 32s in 59? Yes, so we would write a 1 in the 32 spot. So let's see. So then we do like num minus equals 32, right? That's going to give us 27. So we have a 1 in the 32 spot. Are there any 16s in 27? Yes, so we do num minus equals 16, which is going to leave us with 11. Are there any 8s in 11? Yes, so num minus equals 8, which is going to leave us with 3. Are there any 4s in 3? No. Are there any 2s in 3? Yep, so num minus equals 2. And then we need to, so we're left with 1, and there's a 1 and 1. So then we subtract out the 1. So if we look at this value is going to be, well, we have 1, 1, no 2s. Do we have any 4s? No, we didn't have any 4s. Do we have any 8s? Yeah, we had an 8. Do we have any 16s? Yeah, we had a 16. We had a 32, which is, oops, off by something. Or did I miss a 1? Well, 1 would only bring me up to 58. So we should have a, which digit am I missing?
101 on the right. The third.
So 1, 1. Oh gosh, let's just do it with a table because I can actually see that. So, right, we have 1s, 2s, 4s. Oops, other way around, right? Let's make a new sheet. 1s, 2s, 4s, 8s, 16s, 32s, 64s, right? So there was 132, we had 116, we had 18, no 4s, right? We didn't have any 4s, I believe. So 11011. 1. Oh yeah, 0, 1, 1. There we go, 59. So we got the correct value. Are there any questions about figuring out how to convert from a decimal number to a base 2 number? Should be fairly straightforward. So then what happens if you wanted to go from a binary number back to the base 10 number? Yeah.
Same thing, only replace 2 with 10?
No, right? Remember, the value of the number, it's going to be each spot multiplied by the power of 2.
Okay.
Right? So if we had something like this, what would this number be? And what works is to say, what should this binary number's base 10 value be? 64 plus 8 plus 4 plus 1, right? So 64 plus 8 plus 4 plus 1, 77? Unless that didn't work, 60, just, yeah, 77, right? 64 plus 8 plus 4 plus 1. So again, fairly easy to get back to the base 10 value. Just multiply each number by the corresponding power of 2 to the spot that it's at. Just like when you're doing a base 10 number. But use base 2, not base 10. So hex is base 16. Since our digits can take on the values between 10, digits can all go all the way up to 15. The digits 10 through 15 will be represented by the letters A through F, so that there's only a single digit per spot, like a single character to represent a single digit. This kind of gets confused. The reason that we have this is because if we had a value like this, right, is that supposed to be one digit, 10, or is it supposed to be a 1 followed by a 0, right? It would be ambiguous if we used multiple characters for a single digit, which is why we have the letters A through F to represent 10 through 15. So this is actually going to be 16 because it's 116 followed by 0 ones, right? If I wanted 10, be A. I have 10 ones. So when we write our hex digits, especially when we're writing them in the computer, we're going to prefix them with OX to say that they're representing the hex digit as opposed to representing a decimal number. So when you do OX12, right, it's 116 followed by 2 ones, which is going to be 18, base 10, and not 12 in decimal because we put the OX in front of it. We like to use hex as programmers because it's really easy to convert from hex to binary and vice versa. And this allows us to write really long binary strings in about a quarter of the amount of space. This is because every hex digit is worth 4 bits. Why do you think a hex digit is worth 4 bits? 16, right? And 16 is 2 to the 4. So every hex digit ends up being worth 4 bits. So if we want to convert a binary string to hex, you start from the right and you group bits of 4 of the binary at a time together. If you go all the way through in the final leftmost group, it's missing some bits, like there's only like 3 or 2 at the final leftmost group, just put 2 zeros in front of it, and then you'll end up with 4 without changing its value. Then for each group of 4, convert it into its corresponding hex digit. Find the decimal equivalent value, and then I generally go to hex. So if this was our binary string, we're going to break it up into groups of 4. So 1, 1, 1, 0, 1, 0, 1, 1, or 1, 0, 1, 0, 1, 0, 1, 1, and 0, 1. This group is a little bit short, so we add 2 extra zeros to the front of it to pad it out, so it ends up having 4 bits in it. Then we convert each group of 4 into its corresponding hex digit. Here, what's the decimal value of this group of 4 bits? It's 1, right? Because we have 1, 1. So that's represented as 1 in hex. What's the decimal value of this group of 4 bits? So remember, this guy right here is a 1, a 2, a 4, and an 8. So we have how many 8s? 1 8 plus 1 2 plus 1 1, which is 11, right? But we said the digits A through, or 10 through 15 are represented by A through F. So which digit would we use for 11? B, right? Because A is 10, that makes B 11. So we get B there. So here we have 1 8, no 4s, 1 2, no zeros. That's going to be 10, which is A. Then we have 8 plus 4 plus 2, which is going to be 14, right? And then again, you can kind of like go up the letters, right? So A is 10, B is 11, C is 12, D is 13, and E is 14. So we would use E here. And so the answer is 1B. Any questions on doing the conversion? Yeah.
How would a computer convert the numbers to a letter?
How would the computer convert the numbers to a letter? So everything in the computer is represented with what?
Binary.
Binary. So everything in the computer has is binary, right? So the difference is how does it display it to you, right? So when you see the when you see that you have 10 here, right? You want to display A, right? So you turn on the pixels on the screen so they look like an A.
I guess what I was trying to ask was, how do you, like, when you're trying to convert a binary, like binary to decimal or decimal to binary, it's all just math. Whereas if you're trying to convert, like, if you're trying to convert this to hex, you're gonna have to tell the computer somehow to display letters instead of numbers.
But again, like, how is it harder for the computer to turn the characters on the screen into a 1 or into a 0 or to a 2 or to a 3 than change it to the characters that represent an F, right? Change those pixels to look like an F. How is it any different?
It's not, I guess what I'm saying is, how do you tell it to display an F? Because with, like, do you just use ASCII addition or something like that?
So, like, if you found that the digit was 10 and you wanted to show it as hex, you would say print A.
Oh, so you just code it in, like, hard code it.
You put it in. Or if you're working in C and C++, you can do printf with %x. So %x means display the value of this whatever as hex. So if you print like the integer 32 as hex, it'll show its value in hex, which would be 2/16.
Okay, so you hard code it, is what you're saying?
I mean, are you talking about how do I as a programmer write it? Or are you talking about how does the internal circuitry for like not the circuitry, but how does the internal program for the terminal work to display it as that?
I'm saying you give us an assignment where we have to convert different bases to each other. And I pretty much get it for like the stuff where there are no letters, because then it's just simple math. But when you start adding letters in, then you have to say like, you have to basically do it, you have to like hard code it for every possible.
No. So stop by office hours and we'll talk about that question, because I thought you were asking something different here.
Oh, okay.
Any other questions? So let's say we want to go from hex to binary. For each hex digit, find its binary representation and you write it out. Make sure, though, that every time you write a single hex digit, you make sure that you write 4 bits for each hex digit, because every hex digit is worth 4 bits, that nibble, right? So if we wanted to convert 2F1B to binary, well, the binary representation of 2 is 0, 0, 1, 0. F is 15, so there's 1, 8, 1, 4, 1, 2, 1, 1 in it. So we get 3 ones. 1 is, again, 0, 0, 1. And in B, which is 11, it has 1, 8. And after you take out the 8, you're left with 3. So no 4s, a 2, and a 1. 1, 0, 1, 1. Then you write it all out. 0, 0, 1, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. Yeah. In the hex notation, the computer will be happy with either lower or uppercase. So if I do like, what's OXA? It's 10 if I'm writing it out. And if you want to write like a hex constant in your machine, you literally write OX, the bit string, and or the hex string, and it'll give you that numeric value, or that bit string value that you're looking for, just like you're seeing me do right here in Python. Or again, if you want to get like a binary value, it's 0B, 110110000101, right? And you can write that in C and in C++ as well, and it works. Well, I mean, they're both like A is both going to be treated as 10, right? And are you talking about for the change of base one?
Yeah, like another representation, lowercase A and uppercase A is different.
Yeah.
But for the program, you want those to both still equal.
Yeah, so if you want it to be consistent, the easy way is to make all of your letters uppercase or lowercase when you're doing your internal conversions, and then you only have to work with one of them, right? So what's going to be the binary value of, let's see, of OX, say 1, 3, 4, 5, AC. What's that guy's binary value going to look like? So again, if we break it apart, we just have to translate each and every individual character that we have. So 1 is going to be equal to 0001. Well, you should display that when I want you to do 0001. Right? 3 is, right? It's going to be 0011. Right? 1, 2, 1, 1 to get 3. 4 is going to be 0100, which is 1, 4. 5, right? 1, 4, 1, 1. A is 10, right? So are there any 8s in 10? Yep, you have 1 8, and after you take out that 8, right, you're left with 2. So any 4s? Any 2s? Yep. And then we're kind of at 0, so there's A. So C represents, right? So A is, that's 10. C is, what's its decimal value first? 12, right? And then its binary value is going to be 1, 8, 1, 4, no 2s, no 1s. So if you write these guys all out side by side, that gives you the binary value. Any questions here? Oh, well. I thought I gave bin a single value. Maybe, I deleted it. That's why I failed. Right? What would be the hex value of 0010? Oh gosh. 0010 1101 1111 1000. And then maybe we start with this guy. Maybe he just leads with 11. Right? So we have 11 0010 1101 111 100. Yeah.
I'm sorry, can you make the font a little bit bigger?
Absolutely. Well, everything. Big enough? Yeah. So, again, you just break up each of the bits in the bit string into a group of 4 and then translate each one. This is what value?
8,
It's 1 8.
15,
That's 15. 15 is represented using F. 1101, that's 1814, which is 12, plus 11, which is 13. So 13 is D. This guy is 2. And this guy is
12,
not 12. Remember the zeros, right? We're missing some zeros, so where do we put the zeros at? In the front, right? So the zeros would, I don't know why it's not letting me write them in the front. The zeros would go in the front, so you get 0, 0, 1, 1, which is 3. So the answer that we have here is OX32DF8. Right? And so when you're working with like bit string constants, I highly recommend that you write them in their hex value as opposed to their decimal value, because their decimal value, it's hard to figure out what you actually want. Like if I asked you, if we were just using like the bit value of something like 23, do you guys have any idea in your head what it's supposed to look like? Or any way to like conveniently get it? No. But if it's in hex, right, and you saw the value of something like OX2A, right, it's not 23, but it'd be pretty easy to figure out what the bit string representation is supposed to be, right? 2A would be 0010, then the A would be 1010. But it's less to write, and if you do have to figure out like what it actually is, writing it down is easy. This is a lot better than doing it in binary, because sometimes some of the bit strings that you have to write are like 23 or 25 bits long or like 30 something bits long, right? If you're writing a bit string that's like 31 digits long, how likely are you to make a mistake in that? Pretty high, right? And then if anybody else goes to read it, it's just kind of like, you glaze over, because there's so many bits there. Trying to figure out what position they're at is hard. So hex makes it a convenient way to write binary in your programs. So we talked about going from base 10 to hex, base or hex to decimal, hex to binary, binary to hex, decimal to binary, and binary back to decimal. How about just converting from one base to any other? This does show up every now and then, and guess what? It shows up in your homework too. So there's a really simple algorithm for doing this. First, convert whatever base you're given into base 10. The reason for doing this is that we suck at doing math in other bases. And if you're trying to do the math in some base like 7, you are going to screw up, I promise you. No matter how good you are, it's so easy to make mistakes because you've been ingrained to work in base 10 your entire life. And breaking those habits is really hard. So first, convert to base 10, right? Then what you want to do after you convert to base 10 is you divide that new decimal value by the base that you want to convert to. You keep dividing your new quotient by that new base until the quotient finally ends up being 0. Then what you do is you're going to write your remainders from bottom to top, left to right, to get your new answer. And we'll show you what that means in a second. Yeah?
Again, what if they're letters?
Again, the letter, what does it represent? A numeric value. When you get A, it means 10,
So
right?
You're saying that the computer, if I divide A by 10 in C++, will be happy?
No. I mean, you can do it, but A's numeric value in the ASCII chart is not 10. It's like 60-something, right? If you look at the ASCII table, and you look at something like little a, its decimal value is 97, and big A, its value is 65.
Right, so how will that math work on...
So you now have a new subproblem. Convert the letter into its corresponding numeric value. Which again, stop by office hours if you want to talk about that.
All right, I think I'm getting this.
But it's just a new subproblem that you have to deal with in the homework. But it's not that big of a deal. But yeah, stop by office hours for that. So let's say we want to convert 432 base 5 to base 7. Again, converting to base 10 is fairly easy. Just multiply each digit by the current base times whatever its position to its position, whatever it happens to be at. So over here we have 432 base 5, so that's 4 times 5 squared, plus 3 times 5 to the 1, plus 2 times 5 to the 0, which is 117. Right? Any questions on the converting to base 10 part? The next part is we keep doing our division until the quotient becomes 0. So first we divide 117 by 7. That's going to give you 16 with a remainder of 5. Then we do 16 divided by 7. That's 2 with a remainder of 2. Then we take this 2 right here, the quotient, and we divide it by 7 to get 0, remainder 2. And so then we write our answer from the bottom to the top, left to right. So this is going to be 225 in base 7. How could we confirm that we did this correctly? Right, because 432 base 5, it should be equal to 225 base 7. Right? But both of these should also be equal to 117 base 10. So if we tried to figure out what's 225, right, base 7, we convert that to base 10, we should get 117, right? And if we do this out, that's going to be 2 times 7 squared. Gosh, we can do this. Plus 2 times 7 to the 1 plus 5 times 7 to the 0, which, if we've done this right, is 117. So we got the exact same value, right? It's just there are different ways of representing this. Does that make sense? You guys ready to do one on your own? Or any questions about the process first? Yeah.
Is dividing by the base only work if you're already in base 10?
The dividing by the base probably would work in the other base as well, as long as you did the math correctly in that base. I just can't do it. I literally cannot do the math in the other base. That's why I always had the intermediate step of converting to base 10. Or like when you're doing this like in the computer, you have to get it to some representation that the computer can actually work on, so that when you do division, it actually divides it correctly like you want. So let's say we want to convert 354 base, I guess I have to do maybe like base 8 to base. Anybody have another base you want to convert it to? Let's say base 3. So go ahead, try it out. See if you've got it down. Yeah.
Can you move your mouse off the thank you.
Sorry. Okay, but let's do exponentiation that way. Okay, so our first step is to do what? Convert to base 10. So the base 10 value here, right, is going to be 3 times 8 to the second plus 5 times 8 plus 4, which is 236, right? So now we need to convert it to the new base. So when we convert to the new base, how do we do that? First step is to do the division of 236 by, right, so we do 236 divided by 3. That gives us 78, and 236 with a remainder of 3 gives us 2, right? So we're going to get, the first step, we're going to get 78 with a remainder of 2. The next step is to divide 78 by 3, which gives us 26, and its remainder is 0. So we get 26 remainder 0. Then we divide what by 3? 26. So 26 divided by 3 is? Say it again. 8, right, for 24. Remainder 2. 8 divided by 3 is 2 with a remainder of 2. 2 divided by 3 is 0 with a remainder of, oops, not 3, remainder of 2, right? This was right here. This was 236 divided by 3. This was 78 divided by 3. 26 divided by 3, 8 divided by 3, and 2 divided by 3. So our equivalent answer in base 3 is going to be 22202 base 3. So we get 22202 base 3. And again, if we want to check, we can do the multiplication back out, and we should hopefully end up with 236. Right. Ends of 22202 base 3 is 236. So we did it right. Any questions on converting one base to another? Could you use this technique to convert between decimal and or convert between binary and decimal? Yes or no? Yeah, you could, right? Could you use this to convert from hex to binary? From binary to hex? Absolutely. It's just that there are shortcuts for doing those. And so if you're doing it by hand, you probably want to use the shortcut so you don't have to do all the division, because a lot of thinking. Or, you know, with the decimal to or the binary to hex and the hex to binary, grouping them by 4 and then figuring out each individual element is a lot easier than repeatedly like dividing by 2 or dividing by 16 over and over again. So up until now, we've only been working with positive numbers, but a lot of times we deal with negative numbers in the machine. So one way that we might decide to deal with negative numbers is to have one of our bits be the sign bit and the remaining bits be the magnitude, the value, right? So we might say if the first bit is 0, it means the number is going to be positive. But if the first bit is 1, it means the number is going to be negative. So here are your bit patterns, which again, they could be interpreted as unsigned numbers. You don't know until we try to give some meaning to them, some interpretation. But over here, right, we have positive 0, positive 1, positive 2, positive 3. We'll skip this one for a moment. That's negative 1. The one beneath that one would be negative 2. And the one beneath that would be negative 3. This guy right here is negative 0. If you follow along with the pattern, right? Because 1 means negative and its value is 0. Any questions here on sign magnitude? Again, if I asked you, what does the bit pattern 0, 1, and 0 mean? What does this bit pattern mean? What should your answer be? 2. Or I should say, what should this bit pattern be? 1, 0, 1. 5. Negative 1. Something else? What are you missing to be able to answer the question? We're missing context, right? So this bit pattern 1, 0, 1, it could mean 5, or it could mean negative 1, or it could mean something completely different, right? You know, if you got this question, the answer is, I don't know. Tell me more. Right? Because you need more context, because bits on their own, they have no meaning, right? You have to be told how we're interpreting them. So while sign magnitude might seem like the natural, straightforward way of doing things, we don't use it in computers. One of the reasons is because there are 2 representations of 0, right? We had positive 0 and negative 0. But if you compare their bit patterns together, what do you get? Would they be equal to each other? No, right? The bit patterns for positive 0 and a negative 0 would be different. So if you just like, are the bits the same? The values are the same? We would get the wrong answer here if doing that comparison. So you actually have to add in like some special hardware to make sure that it always converted to either be 0 or negative 0, depending on what you want to have happen. Another thing, there's also another method, which is 2's complement, that actually makes the addition and subtraction hardware a lot simpler. And then simpler hardware saves money and also saves energy and saves time. So we like going with that method, which is the 2's complement. The way that you can kind of think about the bit patterns for 2's complement is if you have like an odometer in the car, but you have the old one where you actually have to like wind it forward or wind it back, right? If you go if you start at 0 and you go 1 forward, you would end up at 1, right? If you go 1 forward from 1, you should end up at 2. If you go 1 forward from 2, you'd end up at 3 as you advance, right? Now, if you're at 0 and you go 1 backwards, logically you should end up at -1. If you go backwards from -1, right, you should get -2. Backwards from -2, you should get -3. But since our odometer can only represent positive numbers, when we wind it backwards from 0, we actually get 999, right? If we wind backwards from there, we get 998. But we're going to interpret that pattern, 999 in our system, to mean -1, and 998 to mean -2. And you just keep winding backwards. So you can see this over here on the next slide. So again, here's our bit patterns, right? And here we're going to start at 0. So if we pop over to 2's complement column, if we go 1 forward from 0, we should get 1. If we go 1 backwards from 0, we should get -1. 1 forward from 1, we should get 2. 1 backwards from -2 or -1, get -2. From 2 to 3, from -2 to -3. Now this guy in the middle, right? We have a choice. He'd either be -4 or +4. Here we've gone with -4. Why would we want to go with -4 for this as opposed to +4? Look at the bit patterns. What do you notice about all the positive numbers?
They don't use the first decimal.
Well, then they do use the bit, right? I mean, it's being used there, right? But they all start with 0. And all the negative numbers start with 1. So if we wanted to keep up that kind of pattern, we'd want to put -4 there for it to make sense. Yeah.
So would we just assume it's not -0?
Yeah, this is a completely different representation. This is the 2's complement representation. So one of the advantage of 2's complement is there is no -0. Instead, the bit pattern that was -0 in sign magnitude, in 2's complement, it actually represents -4. Any other questions? Okay. So again, here's seeing all of them side by side, right? And you can see that in each of the number systems, right, as long as the bits start with 0, right, they use the same representation for all positive numbers. But unsigned numbers, they don't represent negative numbers at all. And the sign magnitude in the 2's complement, the different bit patterns, right, they're using them differently to represent different negative numbers, right? 111 in sign magnitude is -3, but 111 in 2's complement is -1, right? So again, if you're given some bits, you never know what they actually mean until you're given some context to interpret them in. Any questions here? So let's talk about negating sign numbers. So for sign magnitude, it's really, really easy. You flip the sign bit, right? If we want to go from -1 to +1, you just change the 1 in the sign bit to 0, right? But if you want, and then you have +1. If you want to go from +1 to -1, change the sign bit from 0 to 1, right? Right. If you want to negate any number in sign magnitude to go from 2 to -2, you just flip the sign bit. Hopefully that makes sense. For sign magnitude, or for 2's complement, it's a little bit more complicated. First, you flip all of the bits, and then you add 1. And when I mean like add 1, I literally mean you do arithmetic in binary, adding 1. Right? So if our starting pattern was 1, 0, 1, 1, if we negate it in sign magnitude, it's 0, 0, 1, 1. So again, they all have the same interpretation as when the first bit is unsigned, or when the first bit is 0. So what does this bit pattern represent if we're interpreting it to mean an integer number? 3, right? So what must this number have meant in sign magnitude? Must have been -3, right? In 2's complement, we flip the bits, 0, 1, 0, 0. So we go from 1 to 0, 0 to 1, 1 to 1, 1, or from 1 to 0, 1 to 0. So we flip the bits, and then we add 1. So 1 plus 0 is, it's not a trick question, 1, right? So 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 in base 2 is, it's 0 with a carry of 1, right? Because what happens when you're in the decimal numbers, right, and you like add 6 and 8 together, what happens? You get 4 with a carry of 1, right? Because when you add 6 and 8 together, you get 14, right? But you can't represent 14 with a single digit. So you get the 4 left over in your spot, and then you get the carry of 1, right? Because you've reached your base, right? We've gone over our base, which is 10, right? The same thing happens in base 2. Whenever you get to 2, right, that just carries a 1 over into the next spot, and you're left with 0 because you took out 2. So here's our example of negating numbers. So for finding the decimal number of a signed binary number, first you find the positive representation of the number. We like to do this because the positive representations of the numbers are really easy to work with, right? So if the number was already positive, great, you're done. Find the value, just convert it to base 10, you're finished. But if the number was negative, you first have to negate your number to make it positive. And then your answer is going to be negative, whatever that number happens to be. Maybe I'm going the other way, right? So first over here, we have negative 12, and we're writing that with 5 bits. So first we find positive 12, because it's really easy to find, right? So positive 12 is, right, no 16s, 1 8, 1 4, no 2s, no 1s. So that's 12. Then we need to figure out what the number is negated. So if we're doing sign magnitude, we just flip the sign bit. That's negative 12. If it's 2's complement, we flip the bits and add 1. So after flipping the bits, we're going to end up with 1, 0, 0, 1, 1. Notice each of the bits in those spots is flipped. And then we add 1. So 1 plus 1 is 0, carry 1. Right? Because it's like, 6 plus 4 is 10, right? Which would leave you with 0 with a carry of 1 because you've reached the base exactly. So 1 plus 1 would be 0 with a carry of 1. So we get 0 here. We carry the 1. So 1 plus 1 is 0. We carry the 1. 1 plus 0 is 1. And then we have 0 plus 0 plus 1. So we get 1, 0, 1, 0. So that's how you'd represent negative 12. Using 5 bits. Any questions here? Okay. Find negative 23 in 7 bits. So our first step should be to do what? Find the positive representation of that number, right? So over here, we have 7 bits. 1, 2, 3, 4, 5, 6, 7. So are there any 64s? Nope. Are there any 32s?
No.
Any 16s?
Yes.
Yes. After you subtract out 16 from 23, you're left with, should be about 7, right? So are there any 8s and 7? Any 4s and 7? Any 2s and 3? Any 1s and 1?
Yep.
Did that not do it right? I feel like I'm missing some bits here. Some leading zeros. 1, 2, 3, 4, 5. Come on. Oh, I didn't want to do an equals sign there. Oh gosh, just let me edit the cell. Delete. Okay, there we go. Am I in insert mode? That's why you keep liking to. Okay. So, gosh, no 64s, no 32s, 116, no 8s, a 4, a 2, and a 1. There we go, right? So, this is positive 23. Now, if we're working in sign magnitude, right, we just have to negate the value. So, what's this bit string negated? 1, 0, 1, 0, 1, 1, 1. Right? We just flip the sign bit. In 2's complement, right, the first step would be to, so flip bits. So after we flip the bits, we end up getting, gosh, here, let me put that in there. We'd get 1, 1, 0, 1, 0, 0, 0. Right? Then add 1. So now over here, we would get plus 0, 0, right? 1 down there. Probably off by some number of zeros, but it's not too bad. And then so over here, when we add 1, we're going to end up with 1, 1, 0, 1, 0, 0, 1. And so that's negative 23 in 2's complement. Any questions? Right? And you could literally write a function, right, in C or C++ to negate a number, right? So if you had something like this, we wanted to define, my negate of, say, x, what would you do? What would you write here? So you want to return negative x. What are our, assuming we're working with 2's complement numbers?
Flip the bits.
Flip the bits. So how do you flip the bits? The tilde. So tilde x. So you flip the bits and then you?
Add 1.
Add 1. That's the function. Right, so pretty simple. Again, if you're working with 2's complement numbers. It won't work in Python, but it'll work in C and C++. Okay. So if you want to go back the other way, so you have some binary, it's supposed to be representing a signed number, and you need to convert it into its decimal equivalent. First, if the binary pattern represents a negative number, write a negative sign to remember that the number is going to be negative, right? Then we're going to flip the bits. Then we're going to negate the bit pattern, right? Because if we have a negative a, after you negate it, you'll get positive a. Positive a is really easy to represent. But if we just remember that it was negative, we write negative, whatever a's value happened to be. It's positive representation. So negate the bit pattern. So if the number is positive, you don't have to do anything. And then again, remember that with negative numbers in both sign magnitude and 2's complement, they both start with 1. But they start with 1s because of different reasons. In sign magnitude, we use that first bit to be the sign, and 1 means negative. But in 2's complement, it just happens that all of our negative numbers begin with 1. It's a happy accident or happy circumstance. Finds values unsigned number, write the decimal value after whatever you put down in step 1. So let's say we want to convert 1011 to decimal, right? And we want to interpret this as, say, a negative number. So the first thing we have to do is negate it. If we're negating it in sign magnitude, what do? Flip the first bit. So this bit becomes 0, and you're going to end up with a 011. 011 is 3, but our original number was negative, so the right answer is negative 3. Right? With 2's complement, we flip the bits. So we go from 1011 to 0100. Then we add 1, 0101. That's 5, a 4 and a 5. But our number was originally negative, so it must be negative 5.
still add 1 when you negate.
Again, negation is the same, right? If we're going from positive to negative to positive, the negation is the same for both of them, right? We said for sign magnitude, you just flip the bit, right? But for 2's complement, you always flip all the bits, and then you add 1, right? That's the method for negation. If you give it a negative number, you get back a positive number. If you give it a positive number, you get back a negative number. Any questions here? Okay. So let's move on to memory a little bit. So on most computers, memory is byte addressable. That simply means every byte in memory has an address. This means that like when you ask memory for some unit, you get back bytes. I want byte 3, I want byte 5, I want byte 1379 in memory, right? You ask for bytes. Each CPU, though, has a word size. The CPU's word size is simply the largest unit that the internal circuitry can process and store. So if you have a 32-bit CPU, the largest numbers that it can add would be 32 bits big. The largest numbers that it can store, 32 bits big, right? Internally in the hardware itself, right? If you have a 64-bit CPU, the largest numbers you could subtract would be 64 bits big, right? And the largest numbers you could store internally would be 64 bits, right? The above 2 points lead to the issue of endianness, which is about how to choose how our multiple byte words should be stored in memory. And we have 2 different options. The first is little endian, and in little endian, we put the least significant byte first into memory. So the least significant byte will end up at the lowest address, and when you see some examples, these will look backwards when you're reading the values. Quotation marks there. Big endian, you put the most significant byte first when you're putting the value into memory. So the most significant byte will end up at the lowest part of the address. This is what's done on the internet, and it will look forwards to you. Intel uses little endian. Both choices are completely valid, right? Really, one's not much better than the other. You just got to make one and be consistent with it. So over here, let's say we want to store the value 1, or 0, 1, 0, 2, 0, 3, 0, 4 in memory, right? So we said each hex digit represents how many bits? Each hex digit represents how many bits?
16.
A hex digit can go up to 15, right, because it's base 16. But each hex digit represents how many bits? It's not 16 bits. 4 bits, right? 4 bits. How many bits are in a byte? 8. So when you look at a memory cell can hold a byte. So how many hex digits would you expect to appear there? 2, right? Because memory is byte addressable, 1 byte big. Each hex digit is only 4 bits big, so every entry in memory should have 2 hex digits to go all the way up to 8 bits, even if some of those bits are 0, right? So let's say we want to store this value at address 100 memory. If we were working with big endian machines, we would put our most significant byte first into memory. So 01, 02, 03, 04, right? And notice our most significant byte of the word ends up at our lowest address, 100. If we're in little endian, we'll put our least significant byte first into memory, and then the other one's coming after it. So our least significant byte is 04. So 04, then 03, then 02, then 01. Any questions about little versus big? Right? This one looks backwards to us, right? But it's only like an appearance. This is just how we're going to put the bytes out into memory. And again, since you'd be working on a little endian machine, when you read this word back out, right? If you're a little endian, you read the word, right? This byte here would go into which spot of your word? The least significant portion of the word, right? So it knows how to read the value back out into memory and place it back in a word because it knows how to put it into memory in the first place. And again, big endian, if it read this byte out here, it's going to put it in the most significant byte of the word when it reads it back into the CPU. No questions, I'll go on. Okay, let's talk about floating point numbers. When we have to represent really large numbers with lots of digits in them, we will use scientific notation, right? So instead of writing the number 10230000000000, right, a much more shorthand notation for that would be the scientific notation, which is 1.023 times 10 to the 11. Or again, if we had 0.000250, that could be 2.5 times 10 to the negative 6. Floating point numbers utilize the same idea, but instead of using base 10, they use base 2. So 1.0101 times 2 to the 4 would be 01101, which is 21 in base 10. Or if you had 1.01 times 2 to the negative 1, that's going to be 0.101, again, all in base 2, which is 0.625 in base 10. Any questions here so far? Okay. So our float itself is made up of 32 bits split across 3 different fields. The first bit is the sign field, and if that bit field is 0, it means positive. It's 1, it's negative. The exponent field is the next 8 bits. The more bits here that we have, the wider the range of values that we can represent, right? We can represent really, really big numbers if we multiply it by a big exponent, very, very small numbers if we multiply by a very negative exponent. But the more bits here, the bigger or smaller the value of your exponent can be, so the wider the range of numbers you can represent. The mantissa, which we're going to see is the M field, is going to be the last 23 bits of the number. I feel like I skipped something. Oh yeah, I did skip a slide. There we go. Sorry about that. So in order to keep things uniform, we need to figure out where the decimal point should be placed. If we have 1.0010 times 2 squared, or 10.010 times 2 to the 1, or 0.10010 times 2 to the 3, they all represent the same number. So out of these numbers, which is the best one?
First one.
So for the first one, why would you say the first one's the best one? Right? I mean, like, there's really not necessarily one that's better than the other, but there's like an infinite number of representations for just this one number, right? If we don't pick one form to represent it. And if you had an infinite number of things, how many bits would you need?
An infinite number.
An infinite number, right? But your computer, is it infinite? No, it's right here in front of me. Must be a finite machine. So we kind of need to settle on one. And we just have to pick some convention. So the designers of the floating point number system, they decided that all numbers should be written in the form 1 point the remainder of the mantissa times 2 to the exponent. So the one that we take would be the first one, because it's always going to be 1 point something, right? Again, the mantissa, the more bits that we have here, the more precision that we have. The exponent, the more bits that we have here, the wider the range of numbers. So we have to pick some balance across our the bits that we use to figure out how we want to divvy them up between, more precise representation, the mantissa, and larger range of numbers, the exponent. So the float itself, it's 32 bits big, and again, we have to figure out how to divvy those bits up. There's the sign bit, it's the first bit, it's bit 31, it's 1 bit big. They said to do 8 bits for the exponent, which are bits 30 through 23, and the mantissa, which is 23 bits, which is 22 through 0. That's the M field from the previous slide. If you go to like a double, the double is basically like the same representation as the float, but they've just expanded the size of the field. So there's more bits for the exponent, there's more bits for the mantissa. So 1.m times 2 to the e looks really nice in how a float is calculated, but that's not really how it works. The exponent field is actually going to be treated as an unsigned number, but we still need to represent numbers that have a negative exponent. So if we have 8 bits, that means we can represent the values between 0 and 255. But we want to split this range up so that half our numbers are negative and half the numbers are positive. So what we can do is we can subtract 127 from that number to give us about an even split of half positive numbers and half negative numbers. This is referred to as the bias. So the actual value of the floating point number that's stored is its 1 point, the remainder of the mantissa, times 2 to the exponent minus 127. Also, if you look back on the previous slide, I might have skipped it. With the mantissa, we don't store the leading 1 because all of our numbers begin with 1 point something, right? And if all your numbers are 1 point something, is there any point to having to store that 1? If it's always there, is there any point to actually physically storing it? No, you just remember that it's 1 point something. And the 1 point, the something is the mantissa. So the actual value that we have stored in the float is its 1 point mantissa times 2 to the exponent minus 127. That's what's there. So let's say we want to convert a decimal number to a float. Here's your list of steps. First, find the binary representation of your number. Second, multiply that number by 2 to the 0. 2 to the 0 is another form of 1, right? So multiplying it by 1. It's not changing the value. Then we need to put the number in normal form, right? It needs to be in the form 1 point something. So we move the decimal point, so it ends up being 1 point something, right? But because we don't want the value of the number to change, right, we have to multiply, we have to either increase or decrease the exponent based on which direction we moved the decimal point to. The value in the exponent field is going to be the exponent plus 127, right? So whatever exponent that you have, add 127 to it to account for the bias of 127 that will be subtracted out. If there are fewer than 23 bits in the mantissa field, we're going to add the zeros not to the front, but to the end of the field. Why do you think we add them to the end of the field and not the front? Right? Remember, our numbers are in the form 1 point something. So if you put zeros here, it would now be 1.000000000m. Is that the same thing as 1 point m? No, right? You accidentally made it a lot smaller. But if we put the zeros at the end after the mantissa, it's going to be 1 point m 0.000000000, which is the same thing as 1 point m. If the number is positive, make the sign bit 0. If it's negative, make it 1. Put your sign, exponent, mantissa bits that you calculated in the prior steps in the correct location in the float, and you're finished. So let's say we want to convert 6.25. The first thing that we have to do is convert it to decimal, right? So 6.25, well, there's no 1s, but there's a 2 and there's a 4 in 6.25, right? And if you think about the numbers to the left of the decimal point, right, they're like times 2 to the 0, times 2 to the 1, times 2 to the 2, times 2 to the 4, times 2 to the 8. If you start going to the right of the decimal point, this guy right here is what? Think about in decimal field. What's the first place to the right of the decimal point when we're working with decimal numbers? It's the tenths place. Then you have hundredths, then thousands, then 10,000s, and so on, right? But if you think about them as powers of 10, right, we have 1/10. How can you represent 1/10 as a power of 10?
-1.
10 to the -1. Or hundredths, that's 10 to the -2. Then thousands would be 10 to the -3, and so on, right? But again, we're in base 2, so this spot right here is what? Not 10. 2 to the -1. 2 to the -1 is 1/2 is 1/2, right? Then we have over here we have to the negative, 2 to the -2, which is 1/4. Then we'd have 2 to the -3, which is 1/8. Then 1/16, then 1/32, then 1/64, then 1/28, 1/256, and so on as you continue down the line, right? The same idea, right? So are there any halves in 0.25?
No.
Are there any quarters in 0.25? Yes, so we get the 1 there. So we start with our number. It's 110.01. Is that in normal form? No. So what do we have to do? Got to move the decimal point 2 to the left. And because I moved it 2 to the left to keep the number the same, I have to multiply it by. That's right. It's 2 to the 2, right? Because we're base 2, right? If we were base 10, right, we'd have to multiply it by. It'd be 10 to the 2. So then our exponent field, right? It's going to be 2 plus 127, which is 129, which is this number in binary. And our mantissa field is everything after the decimal point, which is 1001. So when we write this out, we're going to have our sign bit, which is 0. Then our exponent. Then our mantissa. But again, the mantissa is 23 bits big, but we've used 4 of them. So how many zeros do we need? 19, because 19 plus 4 is going to give you 23. So this is the representation of 6.25. So you kind of know enough now to be able to do the floating point homework assignment, or if you know, you also kind of glance at the next slides. You'll have enough to be able to do it. We'll wrap that up on Thursday and then finish hopefully the rest of the slides as well.
So now at this point, which assignments do we do now?
All of them but the last one.
And do you have office hours today?
Hmm?
You have office hours today?
Yeah, right now.
Oh,
Question about the upper triangular assignment.
Yes.
Is it okay to store like an intermediate solution in a two-dimensional array and then print out the compressed version of that, or do we
No,
need
you
to-
cannot at any point in time expand the matrix from its compressed form.
No. But like, say I'm leaving the two matrix that were.
Yeah, so you cannot create a copy of it that's
No.
fully expanded.
Okay, that's what I'm saying. I'm not doing that.
Okay.
But when I'm multiplying numbers and creating like the sum.
Yeah,
is
you
it okay
have to store those values
in a compressed.
in the compressed format.
Okay.
That's perfectly fine, right? So, right, if you have say 2 4x4 arrays you're multiplying together, you could have 10 space for the first array, 10 space for the second array, and 10 space for your result array.
Okay.
But I should never ever see you make 16 space for anything.
Yeah. Okay. I mean, once you figure out the translations to the one-dimensional array, I guess it doesn't really make sense to use a two-dimensional array.
Well, yeah, I mean, that's the whole point, is to get you to think about, how do we do that translation from 2D coordinates to 1D coordinates? Because the compiler does that for you all the time.
Yeah.
And so this is just, you manually doing it.
Oh, quick question. So I'm the audience, so I'm not in the country, but I really want to ask this.
So do you want to audit the course? So if you send me an email, I will add you as an auditor to Canvas, and that should give you because I kind of need the whiteboard to explain the question to you.
Sorry, it's my question.
No, I mean, your question's not weird. Everybody has that question. So it's not like an abnormal question to have, how do I deal with the characters being in here?
Okay, good.
Yeah, and I do that one every single quarter I teach the class. It's just, it helps to have the whiteboard there to know what we need to do. And so I can't really explain it. Walk it off.
I will see you after.